how about f of x equals 4 times x minus 2 to the power 2/3. And so we're going to go and run through its derivatives and see if we can guess what the graph looks like, and then we'll take a look at the graph, see how we did. So the first derivative here, 4 is just constant multiple, so it just hangs out. And then here I have the chain rule. The outer function is the power 2/3, so we bring the power down according to the power rule, multiply by the base. Drop that power by 1. So let's see, 2/3 minus 1 is 2/3 minus 3/3. That's negative 1/3. And then we multiply by the derivative of the inside, and the derivative of x is just 1. Not much happens there. So we can clean that up a wee bit. How about 4 times 2 is 8/3. And we could then get rid of the negative by putting this in the denominator. So we could say it's 8/3 times x minus 2 to the 1/3. All right. And just thinking about these two right here, let's see. The top function, if we set it equal to 0, then 2 is the only number that's going to give me a 0. 2 minus 2 is 0. So let's see, this one has a 0 at x equals 2. And this one right here, x equals 2 makes it undefined. So note, f prime of 2 does not exist, but the original function does exist there, so this is a critical value. So critical value. And since the numerator is constant, the numerator can't be 0. So this thing does not ever equal 0, but it does have one undefined value. Second derivative, which I think I'll use this to get the second derivative. So multiply, so that's going to be 8/3 times negative 1/3. So I'm going to call that negative 8/9. And then we leave the base x minus 2. Take 1 away from that, so negative 1/3 minus 3/3 is negative 4/3. And then the derivative of the inside is 1, so I'm going to skip that. We can rewrite this a little bit, I guess, by taking that negative into the denominator. So we get negative 8/9 times x minus 2 to the power 4/3. So again, thinking about this here, switch colors for a sec. Let's go black. F double prime at 2 is still undefined, and that's pretty much based on the derivative was undefined. So the second derivative is undefined there. That pretty much happens all the time. I'm 95% sure of that, 100%. So that does not exist. Otherwise, we have a fourth power here, which means no matter what we plug into the base, that fourth power is going to make it positive in the denominator. The numerator is always negative. So otherwise, for other x values, f double prime of x is negative over positive is less than 0, which means this original function is always concave down. So if it's always concave down and we have a critical value at 2, that means we should have concave down. Oops, that's concave up. Concave down, we should have a max at 2 based on this information. Let's draw a number line and think about that a little more. So negative 2 is the only critical number. And so we want to test values on each side of that. So we could pick a nice number like, let's say 0 is a beautiful number over there. And on the other side, I guess we could pick negative 3. Oh, positive 2 is the critical number. I lied. Erase that much. Positive 2 is the critical number. So it has 0 over here, and then 3 over here, and see what's happening. So I want to know what is f prime of 0, and if we plug 0 in here, we get -2, we get the cube root of -2, which is negative. So we get positive over negative. Positive over negative, and so that is negative, which means the function is decreasing toward that. Ooh, is that right? Plug in 0, -2, cube root is negative, positive or negative is negative. Interesting. Okay. And on the other side, let's see what happens. F prime of 3. 3 minus 2 is 1. We get positive over a positive there. And so that is positive. So it is increasing on this side. And I said this is always concave down. What the heck? That seems counterintuitive to the increasing, decreasing thing here. Anybody see an error in my work or my thought? First derivative looks okay. That looks all right. And if I plug in 0 here, I get 0 minus 2 is -2. Cube root of a negative number is negative. So that's definitely negative first derivative, which means it's decreasing. All right. If we plug in 3, 3 minus 2 is 1, everything's positive. Positive first derivative increasing. Okay, do I have an error in the second derivative? Negative, I guess I should maybe write that out in more detail just to be clear. We have 8/3 times -1/3. Nobody's chatting. X minus 2 to the power -1/3 minus 1. So there's my -8/9. -1/3 minus 3/3 is -4/3. So that looks okay. Drop that in the bottom. Oh, yes, I see it now. Okay, so, and then if we can't plug in 2 because the function doesn't exist there, but it's definitely negative everywhere else, so concave down. So this negative part is heading in concave down like that. And then this increasing part has to be concave down heading out. There we go. So it's like this butt cheek kind of graph there. And then we get this pointy part here. And this right here is probably what we call a cusp. We'll take a look at that. Probably a cusp. Yeah, so it all does fit together. It's just not like a polynomial type thing. All right, so let's see, what else can we double check? We can find the value here. What point is that right there? So that would be f of 2. And f of 2 is equal to 0, right? Because we're going to have 4 times 2 minus 2 to the 2/3. And 0 to the 2/3 is 0 times 4 is 0. So because it's concave down, we have a minimum of y equals 0 when x equals 2. So if that's x equals 2, then like throw in some axes here. This would be the y-axis going through there. And let's say that's 2 right there for x. This would be 0. So here's the y-axis. And then we could calculate the y-intercept there by setting this, let's see, plugging in 0. If we plug in 0, we get oh yeah, squaring that. So we would get 4 cube root of 4 times 4. So this value right there would be whatever 4 times the cube root of 4 is, which we could calculate. Let's see, what else can we tell about this thing right here? What's the end behavior look like? And we'll pay more attention to that in the next section. That would be to think about what's the limit as x goes to infinity of 4 times x minus 2 to the 2/3. And bottom line here is as x increases, eventually x is going to be away from 2. So bigger than 2 minus 2 is positive, and we're squaring and taking the cube root, and both the square and the cube root grow. So this is just going to keep growing as we head away. So it's just going to head out like that. Similar thing's going to happen on the other side. I don't think there's much more to do here. All right, let's graph, see if we did okay looking at that. Oh, and then we'll analyze the idea of a cusp here. Explain what a cusp means. Desmos, please. 1. X equals 4 times x minus 2 raised to the power 2/3. And then that value right there, I had wrote down that it was 4 times the cube root. Is this at the cube root? Probably. Yep. Hiding in there. Or we could have done just the 1/3 power of 4, and there's that 6.35-ish that they show up here. Yeah. And otherwise we have that 0 right there. Now the end behavior of this thing, and then the idea about what I refer to as a cusp, this pointy part there. Let's just go up a little higher for y, maybe to like 20, and x, let's out a little more. Let's go negative 20 to 20. Oops. I guess that's not what I wanted. I want negative 10 to 10, much like it was before. You can see it keeps growing. I made mine a little shallower than it was, but I want to think about this idea of a cusp here. And the cusp is related to what the first derivative is doing there. And so what I want to consider is for this first derivative there, so f prime of x was equal to 8/3 times, let's see, what was that, the cube root? Power 1/3, yeah. X minus 2 to the power 1/3. And what I want to look at is what is the limit as x approaches 2 from the right and the left. So I'm going to do the right side first. So that means I'm greater than 2. So like table-wise, if I'm looking at x, f prime of x, so way back to limit explorations before, I'm thinking about like 2.1 and 2.01 and 2.001. I want to get close to 2 from the right side and see what happens with f prime of x. So if we think about that, x is a little bigger than 2. Minus 2 here means I'm going to have a positive number in the bottom. Now that positive number is the 2 minus, so it's like 0.1, 0.01, 0.001. So I'm getting closer to 2, so that means this right here is getting smaller and smaller. And then I'm taking the cube root, which makes it get even smaller. So my denominator is heading toward 0, while the numerator is fixed. So this whole thing is heading to positive infinity on this side right here. So I think that the limit as x goes to 2 from the right side of f prime of x, and we could actually calculate those numbers to see, but that looks pretty good right there, that this is heading toward positive infinity. So what that means is my slope is getting infinitely steep. Now, if we look at the other side, what's going on, So if we try to do the limit, switch color please, there we go. Limit as x approaches 2 from the left side of my function, 8 over 3 x minus 2 to the 1/3. Think about what's going on there with x versus f prime of x. Now here I'm doing like 1.9 and 1.99, 1.999, and so on. Oops, 1.999. And if we take any of these numbers and we subtract it from 2, then just that chunk right there, 1.9 minus 2 is negative 0.1. 1.99 minus 2 is negative 0.01. Negative 0.001. And then we're taking the cube root of that, so it's staying negative. So I have this small negative number. So here I'm heading towards 0 on the left side, the negative side. 8 divided by a small negative number is going to end up being a big negative number. So it's still getting infinitely steep, but negative. So kind of like above, slope is still getting infinitely steep, but negative. And so that right there is the definition of a cusp, that this thing gets infinitely pointy, right? So if this were like a weapon, it's the sharpest point in existence down there. It gets infinitely pointy right at the bottom, which is kind of cool. That's a cusp. Cool, huh? All right, let's see, I think we have time for one more, unless somebody has a homework question. I was going to do a trig function. All right, cool. Kelsey's got a homework question. What section and what number, Kels? Sorry, I called you Kels. Is that okay? I don't know, it just came out. 4.5, number 8. All right, let's look it up. Okay, thanks. Number 8. Okay. So we have this function here, and there are 4 important intervals that based on 3 numbers, A, B, and C. All right, and so A and C are critical numbers for the function, but B is not a critical number. All right, let's check it out. Let's see, 3x plus 4x to the negative 1. Remember that. All right, so this is a rational function. So I just want to think about it in rational terms, although that's a nice way to view it too. That's really 3x plus 4 over x. And we could combine, do the addition by finding the common denominator if we wanted to, right? Put that over 1, multiply top and bottom by x. So then I can also view this as 3x squared plus 4 over x. And just a note about the domain that's always important to think about. Sorry. The domain of this function, x cannot be 0. Right, so that's not in the domain. So right away we know we have these numbers to work with. And as we saw in other functions, if there's an undefined value in one function, then we start taking derivatives. The following derivatives also have that undefined value. So this must be one of the numbers they're talking about. That's probably that x equals b number they were referring to. As far as taking the derivative of this function, I think I like this first version they gave me right there. So I'm going to take the derivative based on that. So f prime of x is equal to 3. And then negative 1 times 4 is minus 4x, drop the power by 1 to the negative 2. And if we rewrite that as a rational function instead of the power here, what's that give us? That gives us 3 minus 4 over x squared. And then common denominator here, x squared, So I can also write this as 3, oops, I'm not laying red there. Color scheme of the day. Green function, blue derivative, red second derivative. So we get 3x squared minus 4 over x squared. And with a rational function, the denominator can't be 0, and that matches what we found earlier. If x is 0, we get a problem. The only way we're going to get critical values of this is if the numerator is 0. So for critical values here, we just set the numerator equal to 0. So 3x squared minus 4 equals 0. So 3x squared equals 4. X squared equals 4/3. So x equals plus or minus the square root of 4/3. And we could rationalize the denominator, I guess. So that would be 2 over the square root of 3, multiply top and bottom by square root of 3. So that would be plus or minus 2 square roots of 3 over 3. So that's the rationalized version. This is the unrationalized. They're both okay. So if we put them in order, like think about this on a number line here, we've got 0 in the middle, causes some disruption here. 0 is not a critical value because the function's not defined there. Critical value, the function has to be defined. And then we have twice the square root of 3. Square root of 3 is like what 1.7-ish times 2. Let's just call it over here. So I've got this negative 2 square root of 3 over there, and then equidistant on the other side. I have 2 square root of 3 over 3. So these are the critical values here and here, and the function is just undefined, right? Asymptote type thing at x equals 0. All right, let's look at the instructions for this sucker. All right, so this function, there are 4 important intervals, yep. And they want us to find A, B, and C in order. So notice they have this interval notation written out in order from negative infinity to positive infinity. So then I would say this one here is my negative 2 square root 3. Actually I like it just as 2 over the square root of 3. That's cleaner. Rationalizing the denominator is sometimes necessary, but it's often overrated. And then this one should be 2 over the square root of 3, positive version. All right. For each of the following intervals, tell whether f is increasing or decreasing. Okay, so then we got to check that out. And usually through an undefined value like that, I think usually there's not a change in the derivative, but we got to check it out. So we got to pick numbers on each side. So that means I need approximations of these guys. So calculator, please. So what is 2 over the square root of 3? So it's about 1.15-ish. This is about negative 1.15-ish, and this is positive 1.15-ish. So that gives me some nice numbers to pick in between, right? I could pick 1 here. I could pick negative 1 over here, and then I can pick negative 2 over there and positive 2 over there to plug in. So then I just want to know what is f prime, negative 2, and really we only care about the sign. So over here, if we plug in negative 2, we get 12 minus 4 is positive over a positive. So this is positive. So that means we are increasing through here. And if we plug in negative 1, we get 3 minus 4 is negative over a positive. So f prime of negative 1 is negative. So we are decreasing. And then f prime of positive 1, so I'll draw the arrow 2 for my visual mind. If we plug in positive 1, we still get about the same thing, 3 minus 4 over positive. So negative over a positive, still negative. So we are decreasing through that asymptote. And then if we plug in 2, f prime of 2 is similar over here. It's 12 minus 4, which is positive over positive. So we are increasing there. All right, so we got that part there, and then we want to consider the concavity, so we need the second derivative, which I don't think we found yet. So it's pretty similar to what we've been doing. That problem is weirded, kind of awkward. F double prime. I think I like this version, so I don't have to use the quotient rule. Derivative of 3 is 0. -2 times -4 is +8. X to the -3, the 8 over x cubed there. And for that one right there, let's see, x can't be 0, we know that, so there's really 2 intervals to consider here. And usually I would say plug in the critical value, but I'd rather plug in something near there. So I would choose to plug in -1 and 1. So what's f double prime of -1? That's going to be negative. So that's going to be concave down. And if we plug in f double prime of 1, then that's going to be positive, concave up. All right, nailed it. All right, take care, everybody. We're done with math for today. We are almost back on schedule. We'll go over a couple more problems like this tomorrow, and then we'll move on to the next section. So take care, do good math. I'll see you soon. Adios.